thanks a lot. It's great to have this opportunity to speak here again. So this is joint work with Richard Stanley, and it's a paper that is already on the archive. It's not as fleshed out in parts as I would like it to be, but it's basically done. And this is related to symmetric functions, obviously, but you don't need that much symmetric function theory to understand it. I hope it is in a way a numeric combinatorics problem in disguise. You see all my slides, right? This is working. Good. So I remind you of the definition of a directed graph, a short digraph. This is going to be the simplest possible way to define it. It's a finite set V of vertices and a finite set A of arcs, and an arc is just a pair of two vertices. I even allow loops, so an arc can go from a vertex to itself. These loops will not affect anything, but it's easier to allow them than to disallow them. So here is a typical directed graph. And you can have two arcs going anti-parallel, so you can have a two-cycle. What you cannot have is two arcs going from exactly the same source to the same target, because it's a set of arcs. So those two arcs would just be one arc. Now, every such digraph has a complement. The complement simply means you keep the vertices as they are, but you remove all the arcs and you add all the non-arcs as arcs. So, for example, because this digraph D has no arc from 2 to 3, its complement has an arc from 2 to 3. But since D has an arc from 1 to 2, its complement has no arc from 1 to 2. So basically, everything that was an arc is no longer an arc, and vice versa. I call this D bar. A digraph is loopless if it has no loops. And a loopless digraph is called a tournament. Well, thanks to Koncevich's talk, you already know what a tournament is. But here is the way I would define it. For any two distinct vertices, there is exactly one arc between them. So it's either from U to V or from V to U. It's never both, but it's always one of the two. So here is an example of a tournament. Here is another example of a tournament. You see, with three vertices, you will have exactly three arcs. The only question is what directions they have. This is not a tournament because there is no arc between 1 and 3. And this is also not a tournament because 1 and 2 have two arcs between them. So the next notation is kind of embarrassing. So if V is any finite set, a V listing will just mean a list of all elements of V in some order with no repetition. So this is something the old guard would probably call this a permutation of V. For me, a permutation is a bijective map. So I keep this. I have to invent a new name for it. But still, the number of those listings is, of course, the size of V factorial. And finally, a Hamiltonian path of a digraph is a V listing. So it's a list of all its vertices in such a way that from each vertex in the list to the next, there is an arc. So in other words, it's a path that contains each vertex. This is the standard notion, maybe just defined in a somewhat non-standard way. Long ago, Redei proved a proposition that has become a popular exercise on graph theory courses. Any tournament has a Hamiltonian path. And I use HAMP as an abbreviation for Hamiltonian path to keep certain formulas a little bit shorter than they would be. Well, so people know this exercise pretty well now, partly because it's so easy. But what people often forget is that Redei actually proved something much stronger. He proved that in a tournament, the number of Hamiltonian paths is odd. And of course, an odd number cannot be zero, so this implies the easy fact. But the easy fact is just a little corollary of this. So here is an example. This tournament has one HAMP, because you have to start at 1. If you don't start at 1, you cannot come back to 1. Then you have to end at 3, and then of course 2 must be in the middle. This tournament has 3 HAMPs because you can go 1 to 3, you can go 2 3 1, you can go 3 1 2. Whenever you have a Hamiltonian cycle, you have many Hamiltonian paths because you can start anywhere you want on the cycle. This tournament has 5 HAMPs, this tournament has 9 HAMPs. The number is always odd. So Redei gave a pretty complicated proof. I regret saying that I never read it in full, partly because there is better proofs now. But it's intricate. It involves determinants, but it's not really algebraic. It involves combinatorics too. It has been translated into English if you're interested in this nice little book by Moon. Later, Claude Berge, I hope I'm pronouncing him correctly, found a more conceptual proof. Still a pretty complicated one, but much nicer. So I would call it a proof from the book. But the main part, so halfway through his proof, he has to show a different theorem, which is also interesting. This is not about tournaments, this is about arbitrary digraphs. And the claim is the number of Hamiltonian pairs of the complement and the number of Hamiltonian pairs of the original digraph are congruent mod 2. For example, this digraph has 3 Hams, and its complement has 1 Ham, and they're both odd numbers. So this theorem, due to Berge, has since become known as Berge theorem. Again, not as known as I would like it to be, but still pretty well known among the kind of enumerative combinatorialists that care about graphs. So Berge's proof uses an elegant inclusion-exclusion to prove this, and then he uses a certain inductive argument to derive Redei's theorem from Berge's theorem. It's a cleaner argument. It's still not an argument I would have easily come up with myself. It's not an argument I would give as a homework problem to students. I've once taught it in a course, so you can find it in English as well, but also you can find it in Berge's books. Incidentally, people have gotten curious about these results recently on mass overflow, and a question has been asked that maybe could have been asked long ago, but it took modern computers to get closer to an answer to it. People have observed that the number of Hamiltonian pairs in a tournament is not just odd. Apparently, it's never equal to 7. And that's not even apparently. You can check that. You can prove that it's never equal to 7. You can also prove that it's never equal to 21 with a lot of computer calculations. Other than this, any odd integer between 1 and 80,000 can appear as the number of Hamiltonian pairs. So you might be wondering so are 7 and 21 the only exceptions? Nobody knows, to my knowledge. So this topic has been sort of smoldering for a while, but independently in 1996, Chow has introduced a symmetric function assigned to a directed graph. He was inspired by what is called rook theory. And this symmetric function has a lot of, it's actually a doubly symmetric function with 2 sets of parameters. People haven't studied it much. I'm mentioning it because what I will be talking about is actually a special case of his symmetric function. But to my knowledge, our results are not special cases of his results. This is a case where things actually have more properties than in general. Also, maybe we just don't know how to generalize them. So the easiest way to introduce what we want to do is what we have called the Redei-Berge symmetric function, simply because of its connection to the Redei and Berge theorems, is using quasi-symmetric functions. So for any non-negative integer n and any subset I of 1 up to n minus I, 1 minus n minus 1, we define the formal power series LIN to be the following sum. So this is basically a way to index all monomials. A monomial of degree n can always be uniquely written as xi1, xi2, xin, where the subscripts are weakly increasing. If the only condition was this weak increase, then this would be the complete homogeneous symmetric function because you would be summing all the monomials. But now you also require some of these weakly increases to be strict increases. So you replace some of these lesser equal signs by strict less signs. And which ones you replace depends on the set I. Basically, the set I tells you which of those lesser equal signs to replace by less than signs. This is a formal power series. It is no longer a symmetric function, but it's a quasi-symmetric function, and it's known as Gessel's fundamental quasi-symmetric function. So, for example, L13, you're looking at monomials with degree 3, and you replace the first smaller, less or equal sign by a lesser sign. Similarly, L14, you have monomials of degree 4 now, but again, you replace the first sign by a less. Now, if you have a digraph D with n vertices, you define its Redei-Berge symmetric function as follows. It is the sum of those LINs, where n is always the number of vertices, and the set I is the so-called D descent set of W. So what is a descent set of W? And the sum is over all V listings, so it's over all ways to list the vertices of the graph. So this D descent set of W is the set of all I, such that the i's and I plus first entries of our list form an arc. So basically, every you walk around the digraph according to this list W, and every time you use an arc, you put a strict less than sign. Every time you don't use an arc, you put only a less or equal sign. This is the things we're summing up. So here is an example. D is this little graph 1 to 3. As I said, the loops are not important. You can just forget about them. I'm just drawing them to show you that they're allowed. So UD is the sum of L does WD3 for all the V listings. There are 3 vertices, so there is 3 factorial of these listings. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. And I have to compute the descent sets. What is it for 1 to 3? If I walk around the digraph like this, 1 to 3, from 1 to 2, I'm using an arc. So at the first position, I have a descent. So I have to put 1 here. But from 2 to 3, I'm not using an arc. When I go along 1, 3, 2, I don't use any arcs. So the set will be empty. 2, 1, 3. If I traverse the digraph this way, I'm also not using any arcs because using an arc backwards does not count. Arcs are directed. So 2, 1 is not an arc. So the descent set of 2, 1, 3 is again empty. And so on. So you end up with a lot of empty sets here, but sometimes you end up with an element. And if you sum things up, you get this explicit formula. It's a power series. Of course, if you have finitely many variables, it's a polynomial, but I'm working in infinitely many variables just in order not to push myself, not to have to decide how many variables I need. So this is a typical thing you get as this UD. And there is a way to restate this definition without using Gessel's fundamental quasi-symmetric functions. It is maybe more familiar to some graph theory people because it looks, if you squint very hard, it looks like a chromatic polynomial, chromatic symmetric function. Because what it is a sum over all functions from the vertex set to 1 to 3. And of course, such functions can be viewed as colorings, not proper colorings, just colorings. So they can have equal monochromatic edges. And then you sum the monomial where you basically multiply X color of each vertex for each vertex. So in other words, if the color I gets used K times, you have Xi to the K. But then you have this coefficient. And this coefficient ADF for a given coloring F counts the number of V listings that traverse the vertices in the order of increasing color. And that have the extra property that every time you walk along an edge, the color has to strictly increase. So in particular, you might notice that if the coloring uses distinct colors, so if there's no 2 equal colors, then there is only 1 such V listing because this inequalities uniquely determine the order in which you traverse the vertices, and then this condition is automatic. In that case, you have a 1 here. But if the coloring is, I would say, less wasteful, then you get more complicated coefficients. If you've seen p-partition enumerators, you will have a déjà vu here. I don't want to go into the details because honestly, I don't understand those details myself. There is a similarity. I cannot say how much what it actually means. There is yet another way to restate the definition of this coefficient, and this brings us back to Hamiltonian path. Because if you have a coloring F, you can have for every color J, you can look at the induced subgraph where you take only the vertices of color J. You forget about all the other colors. And then you take the complement of that subgraph and count its Hamiltonian path. And then you multiply these numbers over all possible colors. The result will be ADF. This is just a restatement of this. Because, of course, when you have, if you're listing the vertices by increasing color, you have to first list all the vertices of smallest color, then all the vertices of next smallest color, and so on. And the second condition means that every time you list the vertices of one color, you cannot use any arcs. So you have to walk along a Hamiltonian path of the complement. Anyway, one easy consequence of all of this is that you can count Hamiltonian paths using the symmetric function. Namely, by evaluating it, by setting the first variable to 1 and all the others to 0, you count the Hamiltonian path of the complement. So anything you prove about UD can give you some consequence about Hamiltonian paths. So Richard Stanley came up with this function, I believe, a few years ago, and he did somewhere in his additional problems to chapter 7 of EC2. So what he proved is, first of all, he proved that it actually is a symmetric function, which might sound obvious from the name, but it's not actually obvious from the definition. And he gave certain formulas in some specific cases. I should also say, by the way, that this additional problems, it used to be a file on his website, still is, but there is also a second edition of EC2 out now, which includes those additional problems. Highly recommend. Lots of interesting ideas in there that haven't gotten much circulation so far. Most prominently, this UD includes the chromatic symmetric functions. By the way, this is a typo. I don't mean chromatic polynomial. I mean chromatic symmetric functions of incomparability graphs posets. So if you're interested in those, this is another view. This is another viewpoint on them. So as I said, this function is symmetric, but actually something even better holds. It can be written as a polynomial in the piece. What are the piece? The piece are the power sums. So pk is the sum of the case powers of all variables. So UD can be written as a polynomial in this piece. But, well, what polynomial? Well, it turns out that there is an explicit formula. And to state it, I have to first introduce a convenient notation. If I have a digraph, and I can look at the symmetric group SV on the set of vertices. And for every permutation of the set of vertices, I define P type sigma by as follows. Basically, if the permutation sigma has cycles of lengths A, B, K, then the corresponding symmetric function will be the product PA, PB, PK. I call it P type sigma because the type sigma is the cycle type. It's a partition, and this is the power sum symmetric function corresponding to this partition. Oh, and of course, one cycles need to be included here. Also, we say that a cycle of this permutation is a D cycle if all the pairs, so if you draw the cycle as a bunch of arrows, all the arrows have to be arcs of the digraph. In other words, for every I in the cycle, I comma sigma I must be an arc of the digraph. Now, I can state our first main result, an explicit formula for UD in terms of power sums. Let's read it from here. So let D be a digraph, then UD is the sum of those power sum symmetric functions P type sigma with certain signs over all permutations sigma such that every cycle of sigma is either a D cycle or a D bar cycle. This is a weird condition. I mean, it would be understandable if I said it's a D cycle, but I'm also saying or a D bar cycle. So in other words, if you draw the cycle, either every arrow has to be an arc of D or no arrow has to be an arc of D. But I'm not allowing there to be an arrow that is an arc and an arrow that is not an arc. It has to be one or the other. So what is the sign? The sign, it's similar to the sign of sigma, but in the sign of sigma, you would count all cycles, whereas here you count only those cycles that are d cycles. So here is the formal definition. Of course, this yields that it's a polynomial in the piece. So here is our previous example, but let's compute UD now in terms of using this formula. The cycles of D, if you look at this picture, you don't see any cycles except of the loops, and that's right. The only cycles are the loops. The cycles of D bar are more interesting. There is the loop 1, there is the cycle 2, 3, there is the cycle 3, 1, and there is the cycle 1, 3, 2, but you cannot, for example, 1, 2, 3 would not be a cycle. Note that I identify a cycle with its rotations. So having said 1, 3, 2, I'm not going to say 3, 2, 1 extra. It's the same cycle. Okay, so you're looking for permutations whose all cycles have to be in this list. 2, 3, 1, 2, 3, 3, 1, 1, 3, 2. And if you just write them down, you see that there is 4 such permutations. The signs in the formula are always 1. And the power sum, the p's are here, are written here. By the way, is this line, is the bottom line visible, the one with the p's?
Yes.
I know that sometimes projectors cut these things off. So for example, if you look at 3 to 1, this is one-line notation. So 3 to 1 is the permutation that swaps 1 and 3. And of course, its cycles are a loop at 2 and the cycle 3, 1. And both of them are valid. Generally, of course, a loop is always valid, so this is no surprise. And because the lengths of the cycles are 2 and 1, you get P2, P1. And so you have this formula for UD. Here is another example where you have, so what are the cycles here? 1, 3 is a cycle of D, and then D bar has only loops. It doesn't have any other cycles. So this is more restrictive, and now there is only 3 permutations that, oh, sorry, I was wrong. 1, 3, 2 is also a cycle of D. Anyway, there are now 3 permutations that fill the bill, and there is a minus sign in one of them, so you get a minus in this expression. You don't get a p positive sum. Okay, so here is the formula again. Let's see what it gives us. First of all, it gives us Berge's theorem about D and D bar having the same parity of number of Hamiltonian paths. Because if you look at this condition, it is symmetric with respect to D and D bar. This is also obviously symmetric because it doesn't depend on Z. And this sign does depend on Z, but it's just a sign. Modulo 2 signs do not matter, so modulo 2 you get the same expression for Z and Z bar. What you also get is that if every cycle of D has odd lengths, then the signs are always 1, and so you get a positive expression in terms of the piece. I consider this a bit surprising because I think p positivity is a pretty rare occurrence in combinatorics. Sure positivity is everywhere. H positivity is somewhere, but p positivity is not something I see every day. However, we started this with tournament, so let's see what comes out when the digraph is a tournament. Surprisingly, the result is even nicer. The result is there is a formula where again you sum over permutations, but the sum has gotten much smaller. You sum over permutation sigma, where each cycle is a D cycle, no longer a D bar cycle. Now it's really only about the D cycles. And also, all the cycles have odd lengths. And then again, you have p-type sigma, but instead of the sign, you have a power of 2. And this is 2 to the power of number of non-trivial cycles. So because of this odd lengths, this is not just a polynomial in the power sum, it's a polynomial in the odd power sums, and almost all of them have a 2 in front of them, except for the first one. So I've been told that polynomials like this are actually, this kind of polynomial often comes from a place called sure Q functions, or whole Littlewood Q functions. I don't really see the connection here. So I find it quite surprising that basically the same ring comes out. But also it's a nice result. So even for forgetting about the sure Q functions. And from this theorem, you can easily obtain Redei's theorem because, of course, all these two exponents, if you're working modulo 2, the powers of 2 don't matter. And you're left with the only permutation that has no non-trivial cycles, so that this power of 2 is 1, and that is the identity permutation, for which everything is easy. So our first corollary tells us that UD is P positive when the digraph has no odd cycles. Actually, something even more general holds. It is P positive when the digraph has no cycles of length exactly 2. Cycles of length 4 would be fine, 6 would be fine. It's really just cycles of length 2, so anti-parallel edges. It's only that case in which it can have negative coefficients. So this is a bit of a ziggurat here. So this is the sum over all permutations where each cycle is a D cycle or a D bar cycle, and moreover, no even length cycle of sigma is a D cycle or a reverse D cycle. That's a mouthful. And incidentally, this gives you lots of P positive UDs, and even so, it doesn't give you all of them. Sometimes UDs are P positive for no obvious reason. So let me say a few words about the proofs. I hope they can be simplified a bit. They're fairly long and fairly combinatorial. But let me say a few main ideas. First of all, where does this P-type sigma come from? How do you get power sums at all? The answer is pretty easy. If you've done Polya enumeration, you will recognize it. The power sum for a given permutation sigma is the sum of the monomials corresponding to all colorings, which are preserved by sigma. So all the maps from V to the positive integers such that F composed with sigma is F. This is actually an easy exercise. Now, using this lemma, we can reduce the first main theorem to the following combinatorial lemma. So the combinatorial lemma is this: fix a digraph and fix a coloring of its vertices. Then this number ADF, so the product of the number of Hemps of these complements for each color, is the sum of -1 to the phi sigma. This is the sign that we saw previously over all permutation sigma, where each cycle is a D or a D bar cycle, and the sigma preserves the coloring. So actually, it is probably better to think of the coloring not as a coloring, but as a leveling, so as a filtration, where f of a vertex is like a level at which this vertex lies. And so this equation means that the permutation preserves the level. So the permutation is kind of horizontal. It moves around vertices on a given level, but it doesn't move them between levels. So with this viewpoint, of course, it makes sense to work at each level separately. This allows you to forget about the levels, and now it's really just about a single digraph. So now you have to prove the following lemma. The number of Hamiltonian paths of D bar is the sum of those signs for all permutations sigma, such that every cycle is a D cycle or a D bar cycle. That looks much nicer. So this lemma can be proved using inclusion-exclusion. It's not trivial. You have to do it in some way where this comes out. Basically, every other cycle would lead to a cancellation. This is how it's working, but there are various details there. So this, in the end, this gives you main theorem 1. The other two main theorems can be obtained from one by combining different sigmas into equivalence classes, and then either having them, either just merging them or canceling them, depending on whether the signs are equal or opposite. So for the second main theorem, you define two permutations to be equivalent if one can be obtained from the other by reversing cycles. And this gives you, of course, a power of 2 because the equivalence classes have sizes 2 to the number of cycles you can reverse. But sometimes the reversal of cycles will give you opposite signs, and then everything just cancels. Whereas sometimes it will give you equal signs and you get this 2 power of 2. The third main theorem is fairly similar, but it's not quite as easy because you're not allowing to reverse arbitrary cycles anymore. You only reverse what I call risky cycles. These are cycles of even lengths, which are either D cycles or reverse D cycles. So what either way, you still get equivalence classes with size power of 2. And if there is risky cycles, they cancel. If not, there is only one, so you don't actually see the power of 2 in the end. So you can look up the detailed proof of the first main theorem in the preprint. It also sketches the proofs of the other two. If any of you is involved in formalization, I would be happy to. I see this as a benchmark for formal proof systems because it involves a lot of finicky combinatorics with things like cycles of permutations and lists and manipulations of permutations. So all of it is completely elementary, but it's hard to talk about rigorously. So I would love to see it formalized. So much for the main theorems. Now, here is a little bonus that came out of it without me really asking for it. So Redei's theorem determines the number of Hamiltonian paths in a tournament modulo 2. Can we also say something modulo 4? Yes, we can, and it comes out of our theorems. If D is a tournament, the number of Hamiltonian paths is congruent to 1 plus 2 times the number of non-trivial D cycles of odd lengths, modulo 4. And we have not seen this in the literature so far. Maybe we have not looked close enough. Maybe it kind of follows from something, but to us, it was a surprise. There is also a way to rewrite the first main theorem without speaking of digraphs. So the idea is here that a digraph is like a 0-1 matrix where certain arcs are there, certain arcs are not there. So you put a 0 or a 1 depending on whether ij is an arc or not. You can do something similar for every matrix where you sum over all the V listings and you sum over all monomials. And then instead of disallowing certain monomials, you just multiply every monomial with a given factor, depending on the adjacent pairs in the V listing. And this gives you another symmetric function for which there is a formula like main theorem 1. It is product over all permutations, p type sigma, and then there is a coefficient. So, of course, this generalizes main theorem 1, but it doesn't generalize it in a surprising way. Actually, everything here is multilinear in the entries of the matrix. So if you want to prove it for all possibilities, you can just prove it for zeros and ones, and then you're back to the original case of a digraph. So it's more of a restatement than a generalization. Okay, at this point, I would like to ask, well, obviously my co-author, Richard Stanley, Gerard and Maxime, thanks to all the organizers. A few people have contributed interesting comments. I think at this point, this is not up to date anymore. So I would like to ask for questions before I spend the remaining 5 minutes on on an update to something else. So can we have some questions first?
Yes. So you want us to ask questions, or you will ask questions?
No, you would ask questions.
So, any question?
Actually, I have a little question. I'm familiar with this paper of Agayevsky-Schlossman about 10 years ago when he spoke about some pedestals, which eventually led to what I talked yesterday.
Because sorry, I can hear about every second word you say. You talk about a paper of Agayevsky. What paper?
There was a paper by Agayevsky and Schlossman about 10 years ago about pedestals. It's kind of very something that's very similar to what you are doing. Actually, this paper led to this what I talked yesterday. Yeah.
Oh, okay, that's interesting.
The paper is on the site.
It's actually an archive, this paper, yeah.
Ah, yes.
Yeah.
Is it on the archive?
It's an archive, yeah. It's something called paper.
Thank you. I will take a look at it.
Any other question? Okay, so please continue. You still have about 6-7 minutes.
Thank you. So this is a little update to what I talked about last year, the one-sided cycle shuffles. Again, I can save myself some introduction because Maxim Kontsevich's talk has gone into similar places. Let me just remind you the definition of the things being studied. So we work in the symmetric group algebra over a field of characteristic 0. I wanted to be a field of characteristic 0 because the updates are only about this case. And this somewhere to below shuffles, they are n elements, T1, T2, Tn, defined by this formula. Tl is cycle L. So this is a cycle that this is a 1 cycle, this is a 2 cycle, a 3 cycle, and so on. So basically, every permutation here, it moves L to L plus 1, L plus 1 to L plus 2, and so on, up to a certain point at which it goes back to L. And of course, the 1 cycle is just the identity map. I just write it as the 1 cycle to keep the pattern more visible. In particular, T1 is the famous random to top or top to random shuffle. And in the talk last year, studied arbitrary linear combinations of those TIs. So in a pattern very similar to Maxim's talk, these combinations always have integer eigenvalues. Well, if the lambdas, if the coefficients are integers, they act triangularly on a certain filtration or basis of the symmetric group algebra, and we could describe their eigenvalues. So I want to add a few things. First of all, because triangular matrices have nilpotent commutators, the TIs also have nilpotent commutators. But surprisingly, the nilpotencies are actually the nilpotency happens very early. So for formal reasoning, you would have an exponential exponent here. Ti, Tj to the power of a Fibonacci number would be 0. But actually, a much smaller number is enough. The exponents are actually something bad is happening with the Wi-Fi here, and actually it looks like it's not even the Wi-Fi's fault, it's the whole internet is down here. So I have never tried to give talks from a tablet. This is my first time. Please bear with me for a moment. Can I even share screen from a tablet? Well, I'll find it out now. Does anyone know whether Zoom allows sharing screen from a tablet?
I think this is the same button than
Yeah.
the laptop.
I can't find the function. Well, anyway, it's not that important. I think most of what I wanted to say has been said. I just wanted to add that the question of finding out how those elements act on a given Specht module has now also been resolved. This is very recent. The proof is still being written up. The answer has to do with certain little Wood-Richardson coefficients. So there is a certain skew partition related to every Laconer subset. And if you want to know how the corresponding eigenvalue, how often it appears on a given Specht module, the question is the little Wood-Richardson number of that skew partition and the partition corresponding to the Specht module. Okay, I think I'm mostly out of time, and thanks a lot for being there, and sorry for the break.
Okay. I'm not sure if the question can be still asked from the audience, but you
yes,
can.
Of course. I just cannot show slides. I can answer, I just cannot show slides.
Okay, so please ask the questions. Any questions?
Yes, did you have a better look with the Q analog of Justice Murphy? Because you have a Q version, you know, of Justice Murphy elements. With something
do you mean in the Hecke algebra?
Yes, exactly. But is it help for you to filter by the powers of Q?
I'm not sure how exactly it would help. So Nadia and I are currently trying to extend as much as we can from our work into the Hecke algebra. It seems like the results actually still work there. Maybe not the representation theory part, but the identities seem to work. So far, we have proved very little about that case. I'm not that familiar with the Hecke algebra, and Nadia isn't either.
Okay, any other question? Gleb.
So if we have some specific graph, for example, this famous perfect graph, and
what graph?
Perfect in the sense of birth.
Mm-hmm.
So make some orientation and then consider functions. So this it would be something interesting. Have you check your symmetric function for some famous graphs in other systems?
Not really, but like certain cases have been done before by Stanley. Paths have been done, incomparability graphs of posets have been done. We have not really looked at directed versions of undirected graphs. It would probably be interesting. We haven't thought of that.
Okay. Any other questions, comments? If not, we thank the speaker. So this session is now closed, and that's the thank you very much.
Sorry, I can't hear you. The audio is rather bad right now. Now I can hear you even less.
Thank you for your talk, dear Darij.
Yeah, camera on number.
I don't know. I tried to reach you during the break. I tried to reach you on the Drexel league. Yes. Is it the right place?
Enjoy the dinner.
Thank you. Thank you, dear Darij.